Hello, everyone. This is George Coates, Technical Director with World Auto Steel. I'm joined by my esteemed colleague, Neil McGregor, Chief Engineer with Ricardo, who's been our partner in our steel emotive journey.
Mm.
And hello, Neil. Good morning. Good afternoon for you.
Yep. Hello, everybody. Hi.
Yeah, so today we're going to have another conversation, the second in our series of steel emotive conversations. Today we're going to talk about the materials utilization that was used in steel emotive. And so let's go ahead and get started. Lori, if you'll go ahead and pull up our slides. Yeah, so many of you are familiar with what's described as the global formability diagram. It's shown here on the slide. You're also known historically by the term the banana curve or the banana chart, and that's because of the ellipsoid formations shown by all the different grade or product families available from the steel industry. So right here, you can see that there's a huge amount of different product families that represent advanced high-strength steels and non-advanced high-strength steels, and they have you can see there's overlapping properties, which means that the designer or the engineer can pull different grades and evaluate very different grades for the same functional characteristics. Neil, given this kind of breadth of capabilities, how that affect your design and material selection?
Yeah, I mean, from an engineering perspective, we're looking for lots of different characteristics and attributes in materials. And then you'll see later in the steel emotive design, we're needing strengths in materials, up to sort of 2,000 megapascal. And so the latest advanced high strength steel grades enable that. And then there are, parts where we have kind of complex geometries where we need high formability or elongation. And then we can operate in another part of the formability diagram on the top left where we get the higher elongation. And there are times where we need kind of, high strength and formability. And you can see there, some of the grades, some of the latest third generation grades and the TWIP grades enable that as well. So really, the steel portfolio that's available to us on steel emotive and to any engineers working in automotive, there's a fantastic kind of starting point for you to work with on your automotive structures.
Yeah, that's great. You mentioned the term portfolio. Let's talk about
Yeah.
that for a couple of minutes. For the attendees here, you'll see the evolving steel grade portfolio represented by this slide. In the very first large vehicle program developed by World Auto Steel, it was termed the ALSAB, the ultralight steel auto body. There were only about 11 grades of high-strength steel and advanced high-strength steel. In fact, the first dual-phase steels were being introduced to the industry, and that's 25 years ago. Our most recent program before Steel Emotive was termed Future Steel Vehicle. It was a purpose-fit body electric vehicle or a battery electric vehicle. And we had 26 advanced high-strength steel grades available to us in that portfolio. But as we moved from that time frame, 10, 12 years ago, into the steel emotive journey, and we enlisted members to really dig deep and to develop, show us their grade availability as well as those that were in development. We developed a portfolio for the use by Ricardo that had 64 different, uniquely different AHSS grades, and they're shown there in that table on the right. So Neil, that can be an overwhelming list of materials.
Yeah.
How did that help you?
Well, like I say, going back to the formability diagram, it gives us a fantastic array of materials to choose from. We can use the right material in the right place. So although it looks overwhelming, 64 grades, I think in the final design of body in white, we used 18 distinct or unique steel grades in the final design. But having that breadth kind of allowed us just to kind of fine tune the design, really optimize it for cost, weight, performance, and sustainability. as we'll see in this presentation and some subsequent presentations as well. So yeah, it's a great kind of what we call toolbox for engineers to work with the advanced high strength steel portfolio.
Yeah, thank you. So then we took that portfolio, of course, and Ricardo, through your engineering decisions, right? You're looking to optimize gauge, grade, geometry, the three
Mm-hmm.
Gs. You developed this body in white, or this body structure, and the pie chart illustrates the materials utilization. And there's some bullets on the right. Can you make some comments about the body structure?
Yeah, so what we're seeing here is the final design of the steel emotive body in white structure. So this is essentially the culmination of, like, almost like 2.5 years worth of engineering, tuning and putting the right steel in the right place. So this body in white is purpose designed for a fully autonomous vehicle. So it takes into consideration all of the design requirements of an autonomous vehicle. It looks a little bit different than a conventional body in white. You can see that there's no B pillar. We took the B pillar out and we put that in the doors to give us some better access. The body is stamped, fabricated, high volume for high volume production, consisting of around about 204 individual parts. Like I say, using that portfolio of 64 grades, we used it allowed us to put the right steel in the right place. So 18 unique steel grades in it. It consists of some very, very high strength grades, as you can see from the pie chart. So over 66% by weight of the grades in that body in white are above 1,000 megapascal UTS. So some very, very high strength in there. And what we're seeing there is essentially one design of the body in white, the core design that we called it. So obviously, with having so many grades available to us, there's kind of more than one way of kind of designing the body. So within the Steel Emotive program, we developed what we call an alternative grade specification. So where there might be, steel technologies more applicable in use in Asia, for example, where maybe hot forming is not so widespread, we would use more martensitic grades. So there is another variant of the pie chart and the steel grade usage that we can see there. But from that pie chart, you can see, just under 50% of the body in white consists of press hardened steel and martensitic steel, so ultra high strength steel. And we'll see maybe from this presentation, the subsequent presentations, the reason for that really is the strength required for mainly the crash or frontal crash and side crash requirements. But we'll see that
Yeah,
in
and I'll just add to that. The vehicle is really short. It's a very small profile, right? And as a result, I think it was a huge goal of ours to maintain that small space for maneuverability purposes, right? Because this is purpose fit for ride sharing. And so you want to get these
Yep.
vehicles in and out of the curb. I remember you achieved a really small turning radius,
Yep.
but that was one of the key challenges, right? To manage the front crash with such a short front end.
Absolutely, and that we'll cover that in another session. We'll go into that in a lot more detail. But
I also like the note on the slide, the average tensile strength. I know when we've shown this to OEMs in our technical transfer sessions, that they've been pretty impressed by that. They've generally comments that we've heard of, they've not seen
yep.
body structures with that kind of strength level. Generally, a high number might be around 1,000 megapascals. So this is quite a representation of the high strength capability of the steels, right?
Yep, and that's right, and we can completely justify that, why we've had to use so much, ultra high strength steel. And again, we'll cover that in some later presentations.
Okay, great, thank you. And then this is more of a breakdown, kind of that same pie chart now represented in the structure, right?
Yeah, just showing a bit more detail exactly where we've used those different grades of advanced high strength steel. So you can see in the top left where we've used press hardened steel. So Here we're using, steels with a strength of 1500 to 1900 megapascal UTS. Where we need that strength and where we've got more complex geometry, so where we can't cold stamp it, we use press hardened steel or hot forming to give us that that ultra high strength steel and enable us to form the geometry. In the orange color are the martensitic grades. So these are the ultra high strength steel grades that can either be cold stamped, roll stamped, or roll formed. So these are more the geometry is a little bit simpler, and it allows us to make those either from cold stamping or roll form roll stamping.
Mm.
The dual phase and the complex phase. So yeah, a lot of that's still used in the steel emotive body structure. Again, gives us very good strength for cold stamp, roll stamp, and roll forming. The yellow parts in the bottom left, these are the latest what we call third generation or retained austenite grades. And these are the grades that I referred back to where we need good formability, cold stamping, and hydroform parts with good strength performance. And then in the bottom right, so high strength, low alloy, and bake hardenable grades. I mean, these, you can still get up to kind of 700 megapascal UTS here, but these are mainly for kind of exterior panels, A surface, B surface panels, where we don't need so much strength, and maybe where we just need stiffness. Yeah, so it's all about using the right grade in the right place, and yeah, hopefully through this slide and some of the subsequent presentations, you'll get a bit more of a flavor and understanding of why and how we've applied those grades.
And you mentioned that there was a primary bill of materials, essentially, right? That last pie chart illustrated.
Mm.
But you noted that based on regional availability, particular OEM interests, maybe even their fabrication capabilities, that there are alternative grades. And so there was a secondary bill of materials produced. Is that right? As an example?
Yeah, that's right, and that's all detailed in the engineering report. Unfortunately, we don't have enough time to go into that today, but the audience is, very willing and able to download that engineering report, and the whole details of the secondary bill of materials can be found in that engineering report. Yep.
Okay, great. Thank you. Um, and then, yeah, Neil, so you talked about the tunability of the advanced high-strength steels here. I think this certainly illustrates that.
Yeah, so we've got, we had a 64 grades available, but the other dimension to that is the gauge thickness. So each of those 64 grades is available in a number of different thicknesses. So as well as being able to tune the grade, so the strength, the formability, ductility characteristics for what we need, we can also tune the thickness of that. That allows us to get the strength and the stiffness that we need in the specific regions of the body in white. And so the images that you see here just to kind of show the distribution of the gauge thickness throughout that body in white. So the average thickness is around about 1.23 millimeters. And you can see that we've used gauge thicknesses of, down to 0.5 millimeters, where we've got, particularly large panels, which are more weight sensitive. And then we've gone up to 2.4 millimeters. An example of that is in the suspension towers in the rear, where we need some additional durability, fatigue strength. So it allows us to go up to 2.4 millimeters in those regions. So it's another dimension, another kind of element that we can use as engineers to tune and optimize the body in white structure.
How about all the different fabrication methods that were available to us? So this certainly is a body structure that's not just cold stamped.
Yeah, another dimension. So as well as the grades, the gauge thicknesses, for those 204 parts, there's these different ways of actually manufacturing or fabricating those parts. So processes like roll forming, roll stamping allow you to form uniform or mainly uniform sections. Gives very good material utilization, so low scrap rate. giving us very good cost and very good sustainability performance. The same with hydroforming or tube hydroforming gives us kind of uniform sections with good stiffness and strength performance, and again, good material utilization. Tailor welded blanks allows us to kind of fine tune material in the right place and make a single blank from a number of different material grades and thicknesses. Hot forming, as I mentioned, press hardening allows us to achieve those complex shapes where we need ultra high stiffness, kind of 1500, 2000 megapascals. And cold stamping, kind of the standard, the more conventional method of forming fabricated steel structures is also used widely. So we used all of these on the steel emotive structure. And then maybe if you bring in the pie chart, George, we can have a look at that distribution. So yeah, so 55% of the body structure is cold stamped, but you can see we used a significant amount of alternative fabrication methods. So 31% hot forming, 7% roll forming, roll stamping, and 2% hydroforming. So that really allowed us to kind of again fine tune the structure, giving us good stiffness, strength, cost optimization, and sustainability optimization as well. So really, using all of the grades, the gauges, and all of the fabrication methods available to us to achieve this highly optimized body in white structure.
Neil, just as a reference, the Future Steel Vehicle Program used, I think, 79, almost 80% conventional stamping. So the fact that we were able to really introduce quite a bit of non-conventional or alternative fabrication processes, I thought was really great, because as you mentioned, the high materials utilization factor associated with many of these, that really means you're producing less steel, which means your costs are lower, and as you said, your emissions are lower. So it's a win-win. Can most of these processes or all these processes be found in current manufacturing infrastructure?
I mean, yeah, certainly our experience is, these days most of these fabrication processes are fairly widespread and available to most manufacturers these days. So yeah, they're widespread available. Yeah.
Okay, great. Well, that's really what we wanted to talk about today. The future subjects in our next event, I think we're going to focus on perhaps front and side crash, where we can get into the details associated with the grade selection, the very high utilization of these high strength materials to help manage those crash events. And you're going to find that we really tested this vehicle against all global high-speed crash regulations to make sure that this thing could be on mixed mode traffic conditions on any road.
Mm-hmm.
So, Neil, always a pleasure talking to you and getting your insights here. For everybody that's attending, if you'd like to access the engineering report, you can download it via a link that's that will be shared here, right there. I think you can see it on the screen.
Yep.
And if you have any trouble with that, you can certainly reach out to Neil and I, and we can make sure that you get the link and you have access to all that information, because there's quite a bit of detail regarding the development journey that we've been on. Neil, any further comments?
No, just lots more to tell. So stay tuned for the next episode, and we'll talk more about how and why we use those grades in much more detail. So yeah.
Perfect. Thanks, Neil. And thanks everybody for attending today.
Thank you very much. Bye-bye.
Bye-bye.